Let's now discuss the volumetric flow rate of a Casson fluid in a cylindrical pipe. So last time, we discussed the constitutive relation of a Casson fluid, which is how magnitude square root equals to the square root of the yield stress plus a constant multiplied by the magnitude, the square root of the magnitude of the shear rate. And we also derived the volumetric flow rate of a generic non-Newtonian fluid, which is Rabinowitsch equation. So we recall Rabinowitsch equation. Which tells us Q equals to pi r cube tau w cube, and the integration from tau w to 0 tau square gamma z, and tau squared rz, so tau rz squared. Gamma is a function, gamma dot f is a function of the shear stress and integrated over the shear stress. So we are going to use this equation to figure out the volumetric flow rate of a Casson fluid. That means we are going to use the constitutive relation of the Casson fluid. But before we substitute in the relation, let's just get something straight. So first of all, we recognize that for the Casson fluid, unless you have tau being larger than tau naught, otherwise you would, being larger than tau y, the yield shear stress, otherwise you wouldn't see a flow. So this is the condition for a flow. So that means when we use the Rabinowitsch equation, we cannot integrate from tau w to 0. Instead, we need to integrate from tau w to tau y, because that's the range where the stress range is valid for a valid flow for any non-zero fluid velocity. So we would have Q equals to pi r cube tau w cube. So the upper limit switch to tau y. So this is where we are going to work with. And to simplify the notation, we are going to drop the subscript RZ for the rest of the derivation. So we will just use tau to refer to the shear stress in the pipe. And notice that for the pressure-driven pipe flow, actually negative, and the gamma dot is also negative. So means the motion of, we discussed in an early lecture, the motion of the fluid in the pipe is sort of viscous, is like held back by the neighboring fluid. so that it provides like a viscous drag on any fluid in the pipe. And those drug eventually comes from the fixed wall because of the non-zero and non-slip boundary condition. So recognize that all the quantities variables are negative. However, the Casson fluid, the equation on constitutive relation was coming from an empirical relation, and which means only magnitude matters in the empirical relation. So in this sequence, it's the only magnitude. That means when we deal with the Q, we needed to recognize this difference. So in order to resolve this, what we are going to do is make a change of variable. So make a change of so that we let tau become negative tau. We let the gamma dot become negative gamma dot. We still call it a tau and gamma dot. We just change it in a way that we put a negative sign of it. And to that, so that means we have Q. If for every stress, you sort of put an active sign to it, and for all the strain, you also put an active sign to it, your Q will look like this. Minus pi up to the power third. And then you put an active sign to tau W, you basically put a absolute sign on that. And then let's do this. So this is after change of variable, because you will have a negative sign from gamma dot. You also have a negative sign from the tau, and these two negative sign cancels. And the front negative is because you switch tau W into its magnitude, then it gives you a negative sign because it's to the power of Q. So that's why sign matters. And then now we can handle the constitutive relation in a way that we don't need to worry about the magnitude or the absolute sign, because we have already changed our variable. So from the constitutive relation, from the constitutive relation, we solve for gamma. So for gamma dot, because in this Q, what we have is gamma dot as a function of tau. So we want to express gamma dot as a function of tau. So we have gamma dot equal to 1 over s squared tau 1/2 minus tau y, the power of 1/2 squared. So this is just we rewrite the constitutive relation to express gamma in terms of tau. And you substitute this equation into Q. So we get Q equals to minus pi r cubed s squared W cubed. Integrating limit and integrating limit of tau squared multiplied by tau to the power of 1/2 minus tau y to the power of 1/2 squared to tau. So here we have dropped the subscript RZ. And here you can expand this square term will be the same as what you learned in your algebra class. After expanded the square term, then you can put it back into the Q. So we can rewrite Q. Well, this is a typical integration of polynomial terms. So you just integrate the term by term. It's something you all know how to do it. So you will have the integration term by term. It's 1/4 out the power of 4th. Minus 4 half power of 7 4 plus 1/3 power multiplied by tau cube. So the upper limit of evaluation is tau y, and the lower limit of evaluation is tau w. And then you substitute, and then you evaluate at the upper limit and the lower limit, and clean it up. You will get this final relation. I suggest that you verify it on your own so that you feel comfortable with this expression. So this is the volumetric flow rate of a Casson fluid in a cylindrical pipe. And let's see what happens at a high shear rate. The high shear rate limit we discussed last time. We have S squared being approximately equal to mu infinite. That is the apparent viscosity at a larger flow rate. So we substituted this relation into the Q. So we get the Q equals to pi r cube, S squared being replaced by mu infinite. It is not so that we know it's a subscript. And we can also take out the tau w. You can see all the terms within the square brackets are dimensionless. Sometimes when we write terms, we want to group the terms so that you may have some dimensionless terms. They usually, in this context, it refers to a correction factor. or sometimes you may get a dimensionless term or several dimensionless term as some effective coefficient for some process. So this will be our Q. Now, if you feel more comfortable at working with pressure drop instead of wall shear stress, feel free to do that. So in that case, recognize that tau W, the magnitude of tau W is R delta P divided by 2L. So you substitute into that, you will get a Q equal to 5 R cubed mu infinite R delta P 2L. And then you have those terms. Just copy them again. Okay, so you can see that if you recall the posterior equation for the Newtonian fluid, you may wonder how this is similar to the Newtonian fluid. Because for the Newtonian fluid, we have a very clear relation between Q and the delta P. And now with non-Newtonian fluid, and we have a longer term. And if you want to like reorganize this term in a way that is more suggestive, so you can like keep on simplifying and to see what you can get. You have pi r to the power of fourth h mu infinite L delta P. Now you have 1 minus 16 divided by 7. And you have this term. Hopefully you recognize the first term. And see, the thing in the square brackets, as we mentioned, this is a non-dimensional number. So if you put in real numbers, you will just get a number. So you can think about it. This is a correction term due to Casson fluid. This is correction term. So as compared to the Newtonian fluid. So this Q, this expression, you can think about it. It is the Casson fluid analogous of the Hagen-Poiseuille law. So this Q, or maybe let me write down this Q. This Q, Casson fluid spelling A-N-A-L analogy real law. So hopefully you can appreciate this or you can recognize this. So to check whether you like see the difference or see why it is a correction term, let me leave a exercise for you. Homework. Think about it. Under what the conditions does the volumetric flow rate for a Casson fluid? This is the Q. I refer to this Q we just see. Reduce to for Newtonian fluid. So for this exercise, what you need to do is just write down the conditions, the physical conditions of the fluid, for the fluid that make them reduce to Newtonian fluid. I'm just write two words. Okay, that's it.